All right. Hello, my name is James Brawley. I'm a student at CSU Global, and this is my presentation for discussing Board 6. The topic is method of moments. In statistics, it's good to differentiate between population versus sample. So a population is going to account for every possible person or item in the population, where a sample is just going to be a section of that population. An example would be if I was trying to determine how many or what percentage of the planet, or what was the mean of people that had brown eyes on Earth. I would have to count every person. I don't have the time or money or resources to do that. So instead, maybe I could use a sample, a smaller size that would be more manageable with my resources. Okay, what we want to do with a sample is make inferences about the entire population that actually match what the population statistics would be. Okay, when we talk about statistics, we usually talk about descriptive statistics that people can all come to concurrence on. So some of the statistics we'll look at are mean. That's going to be the average of whatever we're looking at. Variance is going to have to deal with the dispersion of the data points that we have. Standard deviation is also going to deal with the dispersion of the data. Skewness is going to be the shape of our data, and then kurtosis is also going to have to deal with the shape of our data. So when I'm talking about these things, if you think about a traditional normal distribution, right, we have a mean in the center. That's going to be the average of our data, and then we have data that's spread out around it. The variance is going to be how spread out that data is. The standard deviation is going to deal with one standard deviation. 68% of our data is within one standard deviation, and so on. Skewness, so let's say I sort of have a normal distribution, but I have more data on the right side. So it looks like I have a tail on the right side of my data. That data is going to have a shape that is skewed to the right. Okay, kurtosis will deal with the shape of how compressed the data is. So if I have a small variance or a small standard deviation where most of my data points are in towards the mean, I would have a higher kurtosis than, say, if I have a big variance or standard deviation and the data is spread out, my kurtosis would be lower. Okay. The reason I'm talking about these 5 specific descriptive statistics is when we get to the method of moments, as we get into the different orders, each order describes one of these descriptive statistics. Okay, method of moments is just one way of estimating actual population descriptive statistics from a sample. Okay, so we're going to talk about first, second, third, and fourth moments. The first moment deals with mean. So for this definition, if n is 1, then I'm dealing with the first moment. Second moment deals with variance, and with variance I can determine standard deviation. The third moment deals with skewness, and the fourth moment deals with kurtosis. Okay, really what we're trying to do is use a point estimate of a parameter theta, and that's just going to be a single number as a sensible value for theta. And then I'm going to work through an example here next to make more sense of what this theta actually is. Okay. From our textbook, from chapter 7, section 2, in the exercises on page 273 is this problem, number 22. Let x denote the proportion of allotted time that a randomly selected student spends on a certain aptitude test. Okay, and then it gives us a PDF, theta plus 1 times x to the theta from 0 to 1, and then 0 otherwise. So a random sample of 10 students yields data. So we're trying to make an inference about the population, all of the students. We could say there's 10,000 students, 1,000 students, but we're just taking a sample of 10, and we're going to use the method of moments to obtain an estimator of theta and then compute the estimate for this data. So when we do this, we still have to find the expected value. So we're going to use the definition of expected value, which is the integral from whatever numbers were between, and then x times f of x dx. So I use 0 to 1 because the function is from 0 to 1. Substitute in theta plus 1 times x to the theta for f of x. Simplify that. So I have expected value is the integral from 0 to 1, theta plus 1 times x to the theta plus 1 dx. Okay, when I take the integral and I simplify it, I get the expected value for this sample is theta plus 1 divided by theta plus 2. Okay, so that's just from the PDF and from the definition of expected value. Now that I have this expected value, I actually want to simplify the equation just using algebra to solve for theta in terms of the expected value. When I do that, I get theta equals 1 minus 2 times the expected value divided by the expected value minus 1. So that's our equation for the estimator. Step 3 is to calculate the actual mean. So that is the sum of our sample values divided by the number of sample values. In this case, our expected value is 0.8. Therefore, the sample mean is 0.8, or the average allotted time that 10 randomly selected students chosen from the population took on an aptitude test is 0.8. So 0.8. Once you have the expected value, we're just going to take that and put it into the equation for our estimator. In this case, the estimator is 3. Therefore, the estimator for the population mean is 3. Okay, so we just went through an example solving for the first estimator of mean. Higher order moments can be solved using the equations above. And so this is where variance, skewness, and kurtosis came in. So on the left, those are just the estimates. On the right are adjusted with the degrees of freedom. And so you can see as we go up in higher order moments, the equations to actually solve for those parameters becomes more difficult. Okay. One resource I used that was really helpful was this website. We look at the references, what are moments in statistics, and intuitive video. That helped me a lot in sort of understanding what a moment was. All right. That's a quick overview. I hope it's enough to get you started, but that is all I have. Thank you.